4.7 Springs and Conservation of Energy. The law of conservation of energy applies to all types of energy, including elastic potential energy. Let's take a look at one example that illustrates this concept. In this problem, you will model a collision and apply conservation of energy to analyze the outcome. A model car of mass 5 kilograms slides down a frictionless ramp into a spring with a spring constant of 4.9 kilonewtons per meter. The spring experiences a maximum compression of 22 centimeters. Your job is to determine the height of the initial release point. At the initial release point, the type of energy that this model car possesses is gravitational potential energy. When it slides down the frictionless ramp, it will compress the spring. At the bottom, the only type of energy it will possess once the spring is compressed is elastic potential energy. We know that throughout this transformation, total energy is constant. So we know that the gravitational potential energy at top is equal to the elastic energy at the bottom. Putting in the equations for these, mg delta y is equal to 1/2 k delta x squared. And we can solve these for the height of the initial release, delta y. Delta y is equal to 1/2 k delta x squared divided by mg. Let's sub and solve. We have 1/2. K is 4.9 kilonewtons, so that's 4.9 times 10 to the power of 3 newtons per meter, times a displacement of 22 centimeters or 0.22 meters squared, divided by a mass, the model car is 5 kilograms, times 9.8 newtons per kilogram. If you punch this into your calculator, you should get 2.4 meters. Therefore, the initial release height is 2.4 meters. Now we want to calculate the speed of the model car when the spring has been compressed 15 centimeters. We know that the total energy is constant. And we can actually calculate the total energy by finding the total amount of initial energy, the gravitational potential energy it possessed when it was 2.4 meters above the ramp. 5 kilograms times 9.8 newtons per kilogram times a height of 2.4 meters, we get a total energy of 119 joules. Now, when the spring is compressed, it will still possess a bit of energy. If it's compressed 15 centimeters, remember that the maximum compression is 22 centimeters. So at that particular point, it's still going to have a certain amount of elastic potential energy, but some of that will be converted into kinetic energy. So at that particular point, this 119 joules of total energy will be equivalent to the elastic potential energy it possesses as a result of being compressed 15 centimeters, plus the kinetic energy as it will slowly start to release this elastic potential energy and convert it into speed. So the kinetic energy is equal to 119 joules minus this residual elastic potential energy. We can sub the equations in. That's 1/2 mv squared is equal to 119 minus 1/2 k delta x squared. Let's solve this for v. In this case, v is equal to the square root of 2 times 119 joules minus 1/2 k delta x squared. Close the bracket, divided by m. Let's sub in our values here. We get 2 times 119 joules minus 1/2 4.9 times 10 to the power of 3 newtons per meter times the displacement. The residual displacement is 15 centimeters or 0.15 meters. Close this bracket. Remember, we're multiplying 2 by everything that's inside all of these brackets, dividing by a mass of 5 kilograms. If you punch this into your calculator, you should get 5.1 meters per second. Therefore, the speed of the model car, when the spring is compressed 15 centimeters, is 5.1 meters per second. Let's determine the maximum acceleration of the car after it hits the spring. Imagine this car is going to hit the spring, it's going to compress. The maximum acceleration will occur when the spring reaches its maximum compression. And this occurs at a displacement of 22 centimeters. So the net force exerted is equal to the spring force. So MA is equal to negative K delta X. Solving for acceleration, acceleration is equal to negative K delta X divided by mass. We can sub in, we get negative 4.9 times 10 to the power of 3 newtons per meter times max compression of 0.22 meters divided by 5 kilograms. If we punch this in, we end up with an acceleration of 2.2 times 10 to the power of 2 meters per second squared. And the direction this will be pointing, if you imagine, it'll be pointing towards the ramp. Let's try another example. Sample problem number 2. A 48 kilogram child bounces on a pogo stick. At the lowest point of the bounce, the compressed spring in the stick has 120 joules of elastic potential energy. As it is compressed, 0.19 meters. Assume that the pogo stick is light enough that we can ignore its mass. Determine the maximum height of the child during the jump following the bounce. So the maximum height will happen when all of the elastic potential energy is converted into gravitational potential energy. So all of this 120 joules of energy is converted into mg delta y. And we can solve for delta y. It's equal to 120 joules divided by mg, which is 120 joules, divided by 48 kilograms times 9.8 newtons per kilogram. If we punch this in, delta y is 0.26 meters. So the child will rise 0.26 meters from the lowest point on the bounce. Now let's determine the child's maximum speed during the jump. Now the maximum speed will occur, max speed occurs when the spring reaches its equilibrium point. And the spring reaches its equilibrium point when it stretches that 0.19 meters above the ground, so the total energy is 120 joules. And at this particular point where the maximum speed is happening, the type of energy the child will possess is kinetic energy plus the gravitational potential energy as a result of being 0.19 meters above the ground. So we can solve for V. V is equal to the square root of 2 times 120 joules minus mg delta y, close the bracket, divided by mass. Let's sub and solve. We have the square root of 2 times 120 joules minus 48 kilograms times 9.8 newtons per kilogram times this residual height above the ground, which is 0.19 meters, divided by the 48 kilogram mass. If we punch this in, we end up with 1.1 meters per second. Let's take a look at our last sample problem. Here we have a compressed spring which is going to launch a mass of 2 kilograms, and it's going to cause it to slide up a ramp. Now it's going to travel a distance of d along this ramp, but the type of energy it possesses at the highest point along this ramp will depend on its height, delta y, above the ground. So even though it's sliding up the ramp, what it will end up with is gravitational potential energy. The first thing we want to do is to determine the elastic potential energy stored in the spring before the mass is even released. So this elastic potential energy is 1/2 k delta x squared. That's 1/2. Spring constant is 250 newtons per meter, and it has been compressed 0.22 meters. If we punch this in, we get 6.1 joules of energy. This 6.1 joules of energy is going to be converted first into kinetic energy. So calculate the speed of the block as it travels along the horizontal surface. So this 6.1 joules, when it's released and it's traveling along the horizontal surface, will be just kinetic energy, 1/2 mv squared. We can solve for the speed. The mass in this question is 2 kilograms. So if we plug this in, we end up with a speed of 2.5 meters per second. The second energy transformation is going to take this kinetic energy and put it into gravitational potential energy as it slides up the ramp. So let's determine how far along the ramp the block slides before it stops. So it's going to travel this distance delta d at an angle of 30 degrees. As it reaches this height, delta y, above the ground. We can use the trigonometric ratio, sine theta, which is equal to opposite over hypotenuse. And we can solve for the distance it travels up the ramp by rearranging this equation, so delta y over sine theta. Our first job is to find delta y. So we know that this total energy, 6.1 joules, eventually will be converted into gravitational potential energy. The amount of height it will have is equal to 6.1 joules divided by 2 kilograms times 9.8 newtons per kilogram. If we punch this in, we get a height of 0.31 meters. So we can find the distance it travels up the ramp by subbing in 0.31 meters for delta y divided by the sine of 30 degrees. If you punch this in, you should get 0.62 meters. Therefore, the block will travel a distance of 0.62 meters along the ramp. Now let's take a look at a couple of related concepts. The first is the idea of a perpetual motion machine. An ideal spring would never lose energy and would continue with simple harmonic motion forever and ever, or as long as you didn't disturb it. Any machine that can continue to operate for an unlimited amount of time without outside help is called a perpetual motion machine. To be a true perpetual motion machine, the machine must be able to run forever without restarting or refueling. A grandfather clock, for example, is not a perpetual motion machine since you must wind it up every now and then. Definition of a perpetual motion machine is a machine that can operate forever and ever without restarting or refueling. The example in the diagram that I have shown is called Newton's cradle. If you've ever seen this device, if you extend one of these weighted masses to the left or to the right, it will possess gravitational potential energy. As it strikes the other balls, it will transfer this energy and send the final mass traveling up towards the air. This system will oscillate back and forth, and it will continue to do so forever and ever. And ideally, this would continue forever and ever, but it doesn't happen. Eventually, it slows down. And the reason why it slows down is because the motion ends up being dampened. Some of the energy is lost. Let's talk about dampened harmonic motion. So far, we have ignored the effect of friction on the motion of simple harmonic oscillators. The friction in a real periodic system is referred to as dampening, and the harmonic motion of a system affected by friction is called damped harmonic motion. The presence of friction means that the mechanical energy of the system will be transformed into thermal energy, and the system's motion will not continue perpetually. We can classify dampened motion into 3 categories: underdamped, overdamped, and critically damped. The definition of damped harmonic motion is periodic motion affected by friction. Please read this section to gain a greater understanding of damped harmonic motion. As well, try the practice and review problems listed.